compact, let's say, m dot. So with PT too high, you will have the m dot will be corresponding with high rho, and see if you have a high rho, it can decrease the speed. And also, if you have a large pressure, you are, let's say, condensing everything, and you will have a shorter distance between the different molecules of air in order to ignite the mixture that you have. Okay? And so we need also to check how we can have this high and how we can have this high in all flight conditions. This is something that we need also to discuss. Now, in fact, the problem with these combustion chambers is that you need to ignite the mixture. So you need to have an igniter. So if you take the combustion chamber we have here, you see there is one igniter. Very often you will have two igniters, one here and one at another position, very often, when you have a larger engine, because this engine is very small. This is an engine of a UAV, of a drone. So on a combustion chamber like this one, you see this is the place where the igniter is positioned. And if you have, let's say 12, so cans like this, tubular, it's also called tubular, it's a tube, or it's a can, or it's a tube, it's tubular combustion chamber. You will have 12 like this. If you have only two igniters, one here and one there, you will have the flame created in the upper chamber and in the lower chamber. So what do you need to do? You need to create, as you can see, a passage between the combustion chambers. So this chamber is, for example, located like this in the upper position and will communicate with the chamber here. This one will communicate with this one, and so on and so on. And it will communicate with this one, with so on. And you see that the flame will pass like this from one chamber to another. This is a solution in order to reduce the number of igniters, and also a solution to avoid that if one of the chambers is extinguishing, that you are stopping the whole system, because the flame is still in the 11 other ones and will come back into the whole system. So with such a chamber, a tubular combustion chamber, you have in fact a very good solution because it's very compact. So you see, you are creating a small space here in the primary zone, and there is no influence from outside. So you have a very small space where everything is limited, and you can create there this recirculation zone perfectly with no influence of what you have there, and so on. But the problem is that it's very heavy, because you need to have this 12 times, 15 times, 20 times, and it's very heavy, and also you will have a lot of surfaces that will create what? Lowering lambda Cc. So it's from a point of view of stability of the flame, creation of the mixture, creation of the flame, combustion efficiency, this is very good. But it's not good from the point of view of mass, not from the point of view of the pressure losses. And another solution is to create what is called an annular combustion chamber. So this is a tubular or a can, and this is an annular, where you have only one combustion chamber that is making, you see the same here and the same there. It's connected over the 360 degrees. Of course, here you see the different injectors. They are all delivering in the same chamber. So they are influencing each other. So you will have a less easy space in order to create the flame and the recirculation and the combustion. But you have much less surface, less weight, and much less pressure losses. So this is let's say, the solution that you are normally adopting today in all gas turbine engines, and not this one. But in gas turbines that are used in stationary applications, still you have sometimes combustion chambers like this one that are sometimes put outside of the longitudinal axis, because it can allow to reduce the speed, and if you reduce the speed, you reduce the lambda, the lambda cc, okay? So this is an annular. And so you see that the tubular has some advantages, because it's stabilizing, creating a better space to have combustion, whereas this one is lighter and delivering less total pressure losses. So what you can do is mixing, in fact, the two types. There is a drawing in the notes. So where you have a cannular that is delivering into an annular. So you have different cannulars over, let's say, this portion of the combustion chamber. You have a tubular, a can, and then the annular is starting. And this is what is called the cannular, or tubo-annular. So cannular, you see can and annular, or tubo-annular, tube and annular. What's in a name? This is a chamber that is first a can or a tube, and after that an annulus, so an annular chamber. I have also to indicate that here we have a very special or very specific combustion chamber. This is a combustion chamber that is called reversed, because you see that the flow is leaving from the compressor, so leaving here from the compressor, entering this space, going there, flowing this direction, entering into the turbine and flowing in this direction. So you see that in the combustion chamber, the speed of the mixture is going into this direction in opposition to the flight direction, if you want. So this is a reversed or inversed combustion chamber. The objective of that is reducing the size of the system, because you see the combustion chamber is outside of the system, and you can put the turbine against the compressor and increase the rotational speed, have a very, very, very compact engine. Like this one, that is a drone engine. This is also typical of what you would have in helicopter engines in turboshaft. And of course, there is one point that we have not yet really discussed. These are the injectors that we have here, that we will spend some time discussing them. And the igniter that is here is just used at takeoff. So when you start the system and when you are taking off. After that, you stop the ignition system that is taking much too electrical power from the engine, and you will restart it only in very severe conditions, like if you fly in a large rain, for example, so in very specific conditions where the flame could be in difficult conditions and where you could go to a blowout of the flame. But normally the igniter is not operational, or is not operating during the flight. So in cruise, the igniter is normally off in an aircraft engine. Okay? So about the fuel injectors. So the fuel injectors, they need to inject fuel like this. And there are different types of fuel injectors. I will describe them more into details in the next lesson, but there are, let's say, 3 big types of fuel injectors. So the first one is what is called a pressure swirl atomizer. So this is an atomizer. So you see that the injector needs to create droplets from a liquid sheet. So you have a liquid fuel entering here. So you have a liquid, fully liquid sheet that is here. And from this flow of liquid, like you have in a pipe, you need to create inside the chamber the droplets that must be decreased in size by, let's say, heating and vaporization, and then finally fully gaseous mixture with the air that is surrounding. So the injectors are, let's say, principally atomizers. So they are creating droplets. So you can call that also a spray. So you are spraying the fuel. And they are so atomizers that are working on the principle of swirl. I will explain you what it is exactly, and with a very large decrease of the pressure. So where you will have a large pressure drop of the fuel. So the pressure of the fuel will here decrease a lot. So as you need to be in the combustion chamber at the same pressure for the air and for the fuel, that means that you need to have a fuel pressure that is at the entrance of the system extremely high. So that means that you need to have a fuel pump that is pushing and that is pumping the fuel to high pressure. Then you have a large pressure drop of the fuel, and then you have so this fuel pressure that is at the pressure of the air in the combustion chamber. Okay? So this is the pressure swirl atomizer. This is what we have here. This is the type of injector that we have here in front of us. There is another type of atomizer that is what is called the air blast atomizer, where you are not, let's say, creating a spray thanks to a pressure drop of the fuel. I will explain from where this pressure drop is coming, but this is just a jet of fuel that is surrounded by, let's say, 1 or 2 jets of air that is sometimes swirling, sometimes not swirling, and this is with the difference in the in the tau, in the shear stresses that you will, let's say, by the friction of the two fuels together, that you will create this atomizing effect by the fuel that is surrounded by a flow of air or 2 flows of air that are coaxial or sometimes also rotating. It depends. So these are both atomizers. So they create a cloud of droplets that will evaporate gradually. You have also what is called a vaporizing injector, or vaporizer sometimes called. This is a fuel injector that can have globally a shape like this one, with here just fuel, maybe a part of air, and where the fuel will, let's say, leave the system in the opposite direction with air that is arriving in this direction. And sometimes you have air that is also present here, or air that can be present, that it can be added